Hello friends, welcome back to the series on physics of solids. In this series, during our various sessions, we have already covered various portions like crystal structure, how the atoms are arranged in a crystal lattice, and what are the experimental techniques which can be used to analyze the crystal structure, the various diffraction techniques, and then we went on to study what is the effect of vibration of the atoms within a lattice, and then we found that this lattice vibrations are a factor of the temperature, and therefore, the study of the heat capacity or the specific heat of the material gains importance. So, in the last session we have visited various modeling techniques to understand the specific heat capacity. It included Dulong-Petit model, Einstein's theorem, and the Debay's theorem. So, that gave us a better understanding of the thermal conductivity of the material, and also how does the lattice vibration governs the conductivity of a material. But during that session, we have told that the properties of solids can be roughly categorized into two phenomena in a fundamental manner. One, which is related to the motion of the atoms around their equilibrium position, and those which are determined by the movement of electrons. So, the lattice vibration we have already discussed, and that was connected to the to the thermal conductivity of the material, and the lattice vibration quanta was named as phonons. Now, we need to deal with the motion of the electrons. When we are talking about the motion of the electrons, anybody will suddenly remember themselves about the conductivity of a material, or suddenly when we talk about conductivity, the metals comes into picture. So, why metals became so much important in our civilization? Because of some of the favorable characteristic which any metal shows. To name few of them, they have got excellent electrical properties, thermal, mechanical properties, and all those properties at our normal temperature and the pressure. The other interesting point about metals is the electrical resistivities at room temperature, right. Now, when we think about the electrical resistivity, it is really an interesting property or an interesting physical property. One of the best conductor is told to be silver. So, of course, there are better conductors than silver. For example, graphene is a better conductor than silver, but we are not going to that range. But if we just confine ourselves to the bulk silver, it has got a thermal electrical resistivity of the range of 10 raised to 16 ohm meter. But so the top of this level, the top of this electrical conductivity regime is for the silver, and then if you go into the bottom range, you have lot of insulators which of which I can name PTFE, the polytetrafluoroethylene, which is having a conductivity of 10 raised to minus 8 ohm meter. So, this wide range of electrical conductivity of say 10 raised to minus 8 to 10 raised to 16, which is of the order of 24. This range over 24 orders of magnitude is of really a huge interest, and that needs much better models to explain them. One of the comparison with this 24 orders of magnitude would be the comparison between the Earth's orbit to the Bohr radius of a hydrogen atom. So, that is the range in which the electrical conductivity of a material ranges. So, we need to put all this material into one single model in which we can understand this kind of a conductivity or the electrical conductivity of the material. So, there has been lot of attempts from the historical times to understand the electrical behavior of solids. So, much of the part has been to model the electrical resistivity of the material, and still work is going on to develop on the models which are available for explaining the electrical conduction. Now, while dealing with the electrical properties of any material, for that matter say metal, if we take, the motion of electron gains significance. Now, to put a similarity between some other physical property, the viscosity could be a very easy example. In viscosity, we are basically dealing with motion of uncharged particles, right. But in electrical conductivity, we talk about motion of charged particles, what we call as the electrons or maybe holes at some point of time. But otherwise, there is a close similarity between the viscosity and the resistivity or the conductivity of a material. So, what is the fundamental rule you know about the conductivity? The easy answer could be, which comes to a mind of a student, could be Ohm's law, V is equal to I R, right. So, which states that the current in the steady state is proportional to electric field strength, and the constant of proportionality leads into a term called the resistance or the resistivity as the way in which you derive the equation. And this and therefore, this constant which is dealing with the resistance of a resistance or the resistivity of a material leads into the terminology called the conductivity, and you know that conductivity is the inverse of the resistivity of a material, and that is a constant for a material at a particular temperature. And then metals do have high thermal and electrical conductivity compared to other materials. Now, when it comes to different models which came to develop the to understand or to explain the conductivity of the material, the first and foremost model which comes into mind is the free electron theory of metals. And in the free electron theory itself, one can classify to some extent two different regimes of explanation, one based on the classical laws and another based on the quantum concepts. The rule which was the theory which was developed based on the classical laws was primarily developed by Drude and Lorentz, and that was in the beginning of the last century. But one should always remember that was a similar time in which the quantum mechanics also got developed, but quantum mechanics was still in its nascent stages, and all over there was an awakening in the field of science to understand each and every natural phenomenon which is occurring, and the classical models were really in the limelight that time, and then the Drude and Lorentz tried to explain the conductivity based on the classical models. So, basically the Drude and Lorentz used electron gas model, this is a statistical model, to develop free electron gas model for conduction. Here one of the foundation stone on which this model is built is the concept that the valence electrons in metals are regarded as non-interacting particles of an ideal gas, right. It assumes that these valence electrons do not interact with each other. But the difference from from the central concept of the ideal gas theorem was that in ideal gas concepts, it is not necessary that the particles are to be charged, but here in the free electron gas model, the difference is that the particles which are participating as part of the ideal gas system are charged, which we call as the electrons, right. So, free electron model mainly deals with properties that are dependent on the kinetic properties of these conduction electrons. So, when it comes to the conduction models, among metals itself, if somebody asks you what is the best metal could be, your answer could be based on your atomic model studies or your periodic table studies. You would suddenly rise up and tell that it is based on the monovalent metals like sodium, potassium, all those things. So, for a monovalent metal, the number of free electrons in a given volume is equal to number of atoms in the same volume. So, it was always easier to start modeling with them, and I should tell at this point of time that the free electron model for explaining the metallic conductivity is most valid in the case of monovalent metals. Now, let us see bit more detail into the classical model. So, now so how we start with that? Now, let us start with a case where we do not apply any electric field, right, because electrical conductivity means you will conceptualize yourself that you are starting to apply an electric field, but let us start without applying an electric field. So, what is the assumption? The assumption is that in the free electron model, the central assumption is that the particles do not interact with each other, right. So, what else will the particle will do? Will they go and stick to somewhere or stay in rest? No, because it cannot be, because that does not give out a stable system. The particle has to move on. So, who told that? That was an offshoot of the kinetic theory of gases, right. In the kinetic theory of gases, you always assume that the particles are in a constant in a state of constant motion, which we call as the zigzag motion. So, this zigzag motion is determined by the by one parameter which we call as the temperature. So, zigzag motion is primarily determined by the absolute temperature with some velocity. What is how much will be that velocity? If you ask me what is the magnitude of that velocity, it will be 0. It will have a 0 drift velocity in a particular direction, right. So, if we assume that the kinetic theory of gases can be applied to the free electron gas, then the root mean square velocity, if you know about the kinetic theory of gases, it will come out to be C bar is equal to root of 3 kBT by m. So, because the kinetic theory of gases primarily is just concerned about the temperature, the effect of temperature and the mass of the particle. Here in our case, in the free electron gas theory, m is the mass of the electron and T is the temperature. C bar is equal to root of 3 kB T by m, and K of course is the Boltzmann's constant. Now we will take up the situation in which you people must have imagined, where you need to apply an external electric field, right, which means that now the kinetic theory of gases has to be modified in order to accommodate this electric field. So, what will happen when you apply a magnetic when you apply an electric field? For example, if we take a copper rod of uniform cross section, say how much, say 1 square meter, is subjected to a field of strength E, capital E, right, normally we denote it by E, applied in a particular direction. Now, the possessive nature of the electron is now suppressed, right, or I can tell you the possessive nature, which means that now the electron lost its control to itself. Who takes the control? the electric field which you applied takes the control of the electron. So, what is the effect of that? The effect could be the random motion or the zigzag motion which was predicted by the kinetic theorem, kinetic theory of gases cannot be processed now. The electric field totally takes the control of that. So, the random motion is discouraged and the charged electrons prefer to have a unidirectional motion in a direction opposite to the direction of the applied electric field. So, in that situation the velocity of the electron gets modified than the c bar equal to root of 3 kBt by m, which was a temperature dependent, totally temperature dependent factor, needs to be now modified, right. So, now the question is that, so this electron is moving, right, the electron is moving parallel to the electric field. Now let us try to visualize ourselves that image when we apply a electric field. So, suddenly the electrons which were moving zigzag now starts moving in one single row, or they follow a queue parallel to the direction of the electric field. But now the question could be, can this particle go on moving forever? The answer is that, or one of the, you can always visualize the picture where these electrons will bump into the cations of the lattice from time to time. So, what is the effect of that? Effect is that you are talking about creating a resistance to the flow of these electrons. Now, let us imagine that the average time between each such collisions of these electrons with the cations be represented by tau seconds. Okay. So, immediately after a collision, we further suppose that the velocity of the electron averages to 0. That means, we are assuming a situation where the electron has no memory of the momentum acquired from the field, that the thermal velocity averages to 0. So, in a time tau seconds, electron will attain a velocity given by minus of E tau by m. It is very easy to imagine from where it came. E is equal to mv divided by tau. Mv is the momentum and tau is the time, and that much is the is equal to the energy of the system. So, the drift velocity is equal to minus of E tau divided by m. Now, the next parameter to consider is the current density. So, what is current? Current means it is the flow, it is a measure of the flow of these particles. Here in this case we have the electrons flowing. So, the current density, which is basically the I by the current by divided by the volume, which means that if we need to calculate the current density, we need to invoke the parameter of particle density or the electron density. So, if I take the particle density as n, so small n is the particle and the electron density. So, the current density will come to be minus of n e into V d, where V d is the drift velocity of the electron. Substituting that V d which we evaluated already, we will get the expression for the current density to be n e squared tau e by m, right. So, current density divided by the electric field which you apply. So, what will that give? That will give you the conductivity of the material, right, because current divided by E will give you the conductivity. Current density divided by the electric field will give you the conductivity in terms of the density. So, current density the conductivity of the material will come to be J divided by E, which is equal to Ne squared tau by m, or current density sigma is current conductivity sigma is equal to Ne squared tau by m, or the inverse of that will give you the resistivity is equal to m by Ne squared tau. So, to much extent the world was really happy about the free electron theory of metals, which was based on the classical model. But there were whole lot of issues which were coming up. As I told in the beginning, this model came in the beginning of the last century. The quantum mechanics was slowly appearing, and then correspondingly there were other phenomena also coming into picture, like we were having good capability to apply the magnetic field and measure the effects of that. The superconductivity was coming into picture. So, now the free electron model, which was purely a classical picture, needs to accommodate all these new phenomena also, which was not really happening. Let me now put forward to you two important drawbacks which led to the later modification of the classical free electron model. The first and foremost I would list as the molar electronic specific heat. We already know what the specific heat means by, right, because we have already discussed what does the specific heat means by. So, let us discuss that itself. So, as I told you in the last session, in many solids the most important types of internal energy are: one, the vibration energy of the atoms about their lattice positions, and second, the kinetic energy of the free electrons. The kinetic energy of 1 kilomole of a monovalent metal can be evaluated to be equal to 3 by 2 RT, right, because it is well known. Kinetic energy of 1 kilomole of a monovalent metal where is equal to 3 by 2 RT. So, corresponding molar specific heat. So, what is the expression for Cv? Then Cv equal to dou u by dou t, right. So, if I take that expression, Cv will come to be 3 by 2 R, which will be evaluated to be something like, if I calculate it in terms of joule per kilomole per Kelvin, that will come to be 12.5 into 10 raised to 3. But this was not agreeable. So, the 3 by 2 RT, which was a product of the classical model or the classical free electron model, was not really appreciable in terms of the real value which was measured experimentally. So, this 12.5 into 10 raised to 3 is nearly something like 100 times the measured value. So, what was the modification needed to be made there? The assumption that the free electrons contributes to the specific heat of solids now needs to be modified. So, in the new model that needs to be taken care. Now, the second thing which was considered as a drawback was the computation of the mean free path. So, what is the mean free path means by? So, mean free path, you know, and when it comes to conductivity, the mean free path is a very important concept, because our tau with which we started our assumption is very much connected to the so called mean free path. So, it is mean free path is the distance which any particle makes between two successive collisions. So, here also we can always try to evaluate the mean free path. So, we have the expression for the resistivity equal to m rho equal to m by n e squared tau, or the tau which is the time connected to that is equal to m by n e squared rho. Now, let us try to evaluate this tau for a non-metal with which we started our assumption, which is copper. So, what all parameters you need? In that formula you need the n value. So, the n which is the electron density or the carrier density in the copper, which is normally quoted of the order of 10 raised to 23 per meter cube, and the resistivity is of the order of 10 raised to minus 8. So, based on that, if I calculate the tau value, it will come to be around of the order of 10 raised to minus 14 seconds, or the mean free path, which is tau into the average velocity, will evaluate to be of the order of 10 raised to minus 9 meter, which is of the order of nanometer. But experimentally, the mean free path was evaluated to be about 10 times the value of this nanometer value, right. It was this value, if I supply that, it will come to be around 2 into 10 raised to minus 9, and the real value is something like 10 times this value, the experimental value. So, I just took two important situations in which the classical free electron model really failed. But there are, of course, there are a lot of success associated with the free electron model. Like yesterday we talked about the Einstein's model. There are a lot of situations in which the Einstein model also won it. There it was for the first time that with an exponential fit was connected to the temperature variation. Here also the free electron model, the classical free electron model could explain lot of features of the conductivity, but there were very obvious phenomena which ask for an improvement in the free electron model. So, but as we go in the history of the science, in that period newer and newer models of the statistical models started coming up. There it was the kinetic theory of gases which was applied, which is connected to the so called Maxwell-Boltzmann model, right. Now, we know that electrons are what kind of particle? They are fermions, right, the Fermi particles, which means that we need to apply the Fermi-Dirac statistics instead of the classical statistics to the free electrons in metals. So, there was a purposeful attempt to apply the Fermi-Dirac statistics to the free electron model, and that was being suggested by the Sommerfeld. So, that derivation and that discussion and much more we will be carrying out in the next session of this series. Thanks for your attention. See you next time.